All right, we're back. We're in Notes 13, page 3. We're going to keep doing some u-substitutions. We're doing something I call balancing the problem. I find that I wish you could see inside my brain for how I'm choosing to do these. So highest powered thing, the denominator is often a good choice. I don't know, the highest powered polynomial. There's just like a lot of options, and experience is the best way to tell you. But like it makes sense to me that the derivative of this will be smaller. So like this is probably something to do with du. If I made this equal u, it's like how am I writing this in terms of u? Like life seems a lot harder. Practice, people. It's what it takes. Fortunately, these types of problems are like a dime a dozen. I bet Delta Math can throw a million of these at you. I don't actually know that's true, but I bet they can. All right, du going to be quantity 2x plus 10 dx. So this time, instead of highlighting, I'm just going to like look and say, I have 2x plus 10. I need x plus 5. That's a factor of 2, so, or 1/2. Depends on how you're looking at it. Multiply both sides by 1/2. And I get x plus 5 dx. So we need to make our substitutions, right? So this matches with this, and then this is going to match with this. And then I didn't highlight this one, but I should have this. I think it's good to go. So this will be, pull the 1/2 out, and then the purple and the blue go together and they're just du. And then this is going to be u. Okay, so this is the one where, so try it, right? Try to reverse the power rule. This is really u to the negative first. If I add 1, I get u to the 0. If I multiply by the reciprocal, I'm trying to divide by 0. Not going to work. That's like your hint that this is natural log. So when you try to reverse the power rule and it fails, if you did everything right, you're just dealing with a natural log. And you should kind of recognize this also. Now for complicated-ish reasons, it's going to be the absolute value. I think x squared plus 10x plus 1 is probably always positive. What's the discriminant? B squared minus 4ac. 100 minus, oh, the discriminant is positive. This definitely is not always positive. It has 2 real roots, so like, we need absolute values. So you put absolute value because the domain of the result, so the domain of the antiderivative, the domain of the result cannot be bigger than the domain of the original. Yes, so the domain of the result can't be bigger than the domain of the original, but you also like, I mean, you can find every value that doesn't make this 0 makes sense here. Every value that doesn't make this 0 makes sense here. So when you find the antiderivative, every value that doesn't make this 0 should be in the domain, because you can find the slope at every one of those points. So the way we deal with that is we put the absolute value symbol, and it takes care of that domain issue for us, because it'll take anywhere it was negative, it makes it positive. The only thing that's still a problem is you can't take the natural log of 0. But if you were trying to take the natural log of 0, it means over here you were trying to divide by 0, and that's not in the domain anyway. So the absolute value has solved our problem. You're going to do that a lot. When you find an antiderivative, if it's natural log of something, it's natural log of the absolute value of something. And you can put it in. Sometimes you can take it out, but sometimes you can't. So safest thing to do, put it in. All right, this one's weird. And I'm going to do this in a certain way. One of my students actually taught me this like a couple years ago. I learned to do this a different way from how I'm going to do it. If there's an exponential, so this is like sort of a rule. It's not always a rule because there's other ways to do it, but if there is an exponential, I don't know, I'm trying to spell exponential. Make it u. Make it u, and it'll make your life so much easier. So what I'm going to do is I'm going to make this equal u. And then when you do that, something weird happens. So I'm going to say that u is equal to e to the radical x, or e to the x to the 1/2 you might prefer. So du is going to be e to the radical x times the derivative of radical x, which is 1/2 x to the negative 1/2, then dx. Okay, so that's like crazy. But is it crazy? Because if you look at this, I'm gonna rewrite it. I'm not really rebalancing yet. I'm just gonna say this is e to the radical x 1/2 dx. I just like rewrote it. Look at what we have. We have almost all of this. I mean, dx, obviously. You always have dx. Then we have this radical x, which is here. We have all the parts, and this is the green thing. Look at that. It like almost is exactly it. The only issue is this 1/2. So let's say that 2 du equals e to the radical x dx. Should I color code? It's like on some level, I really enjoy color coding. I think I never really did it. Like the coloring books, I don't know if they're still popular. They're really popular with adults for a while. Seems like it doesn't seem like a bad idea. All right, so our substitution leads us to this insane thing, to the integral of du. That's it. That's the whole thing. So, well, what do I get if I integrate du? So basically, I'm integrating one. So I sometimes have to do this because I find that really confusing when it's just du. I don't know why. What do you take the derivative of to get 1? You take the derivative of just the independent variable. The independent variable in this case is u, so it's just 2u plus c. And then u was this green stuff here, right? This is u, so we get 2 e to the radical x plus c. What a crazy problem, right? So this is, you're going to want to do that. If you see an exponential in an integral problem, you're going to want to try to let u equal the exponential. It's almost always going to work for you. I mean, they get more complicated. As they get more complicated, you need more strategies, but these are like your opening strategies, right? So exponential, let's try that. If there's nothing super obvious, go for the highest powered or highest degree polynomial, or just straight up the denominator. The denominator is often a very good choice. Things inside radicals, really good choices. Things to the highest power, really good choices. And all of them come, like the choices that you're making are all because of the structure of derivatives. Like when you take a derivative, it's like you tend to like decrease the exponent, and then like the chain rule just gives you extra functions. But those functions tend to be lower degree, they tend to be simpler. So like looking for the complicated thing tends to also lead you toward u. Anyway, I think we are done with this page. You need to practice these, obviously. But anyway, I will be back in the next video to do the next page. So see you there.